So good evening, everyone, and thank you for joining us for this edition of the third edition of the Kenya Mathematical Olympiad training webinar. So today we will be talking about the quadratic equations. We have done 2 other sessions, and before what we did was discuss some questions, Olympiad type questions. Today we are changing the format a little so that we discuss the details of the topic, quadratic equations, and I believe we should have some time to solve a few problems at the end. So I'm going to share my screen. And let me know if you can see the screen. Okay, can you see the screen?
Yeah.
Yes, we can see.
Yes,
Oh.
yes, we can. Yes, we can.
Can you make me a co-host? Maybe I can help you manage the meeting in case. Yeah.
Okay, let me just see. Okay.
Yeah, go to participants and then you will see me.
What I'm doing. Participants. There, I think now it's done. So I believe you're now co-host. So I'll just put it on full screen, then we can get started. So this is we'll talk about the quadratic functions and quadratic equations. So this is basically the list of items we shall cover. Just hold on. So this is what we'll cover. We'll look at a few applications. Where do we use quadratic equations and why are they important? Then we'll discuss the quadratic function and move on to the quadratic equation. So quadratic equations appear a lot in real life. One example here is in the lenses and mirrors. The shape or the cross section of the lenses and mirrors usually follow can be described by a quadratic equation. And in particular, one good use that would be useful in tropical countries, especially, or developing countries, is this use of the solar cooker. And this reflector usually has a shape of, can be described by a quadratic equation function, actually. So another application is in mechanics. When you look at the projectile motion, the height of an object above the ground while in free fall can be described by a quadratic function. This is also true for many of the things, like in sports. When you throw a tennis ball or hit a golf ball, it takes a trajectory that looks like this and can be described by a quadratic equation. If you see water from a hose pipe or water in the fountain, if you have a fountain at home or at school, you can see the trajectory of the water normally takes that shape. In business as well, this happens. You can express revenue as a quadratic function. So this gives a simple example where you have a demand defined by this equation here. So the demand written in terms of price is given by this, and the price depends on the amount, the number of goods in the market. So X counts the number of goods in the market. So if you want to find the revenue, you simply multiply X by the price, which is dependent on the goods, and that gives us a quadratic function for the revenue. And you can see a graph here which describes the function. You can see revenue keeps growing up to a point and then starts diminishing. When there's a glut in the market, the price goes down and therefore the revenue also goes down. And the quadratic function describes this quite well. So here are some useful identities which we will find useful as we go along. Some of them should be familiar. The first one is just the square of the sum of two numbers. So a plus b squared is given by a squared plus 2ab plus b squared. We have a minus b squared is a squared minus 2ab plus b squared, and so on. These last three, the last two are not quadratic functions, but they are useful sometimes because one of their factors is quadratic. And they can be useful when solving problems. So now we get to the quadratic function itself. So this is a function which is defined as ax squared plus bx plus c. A, B, and C are constants, and they are called coefficients. There's someone talking. Okay, so a quadratic function is.
Who did you vote for?
Please mute your mic so that we can have one source of sound. Oh boy. Okay, I think I've muted. So sorry about that. We'll continue. The quadratic function takes this form: ax squared plus bx plus c, where x is a variable, a, b, and c are constants rather, and you can obtain the values of this function at different values of x by just making the substitution for those values of x. So sometimes it's also called a quadratic polynomial. And here are some examples of quadratic functions or expressions or polynomials. So all these are examples of quadratic functions. We can use different variables to express them, not just x. Now, based on this identity here, which we have x plus d squared is equal to or identical to x squared plus 2dx plus d squared. We can apply that as follows. We have this quadratic function, ax squared plus bx plus c. So we pull out a and put everything else in brackets so that now in brackets we will have x squared plus b over ax plus c over a. So this process up here is called, if you only have this part of the equation, x squared plus 2dx, you can complete the square by just getting a half of the coefficient of x and squaring it, then adding it. So the half of the coefficient of x here is d. And then when you add the square of that half of the coefficient, you get a perfect square on this end. So we apply that to this first part of the quadratic equation. So we treat our 2d as BA. So we get a half of this and then square it and add so that this first part becomes a perfect square. But since we have added a term that wasn't there, this b over 2a squared, we have to subtract it again. And that's what we do at the end here. And we group c over a with minus b squared over 4a squared on one end, and then the rest of it is on this left-hand end. So this part now, after completing the square, will be a perfect square, which is x plus b over 2a squared. And then we group this as 4, when you put this under the common denominator, 4a squared, you end up with this expression. Now, if we multiply a throughout, this is what happens. We have a x plus b over 2a squared plus 4ac minus b squared over 4a. So the a squared here, this a cancels out one of the a's, so that you're left with only 4a. And this gives you another way to express the quadratic function. So there's some advantages of expressing it in this form, because you will notice that, for instance, this part that is squared will never be negative. And that can help you determine whether, depending on the sign of a, it can help you determine whether the maximum or the minimum point of the graph. We shall see that in a minute. Okay, I clicked on something. So if we're now going to look at the value of the quadratic function when at the point x is equal to 0. And also we consider what happens to the function when x becomes either large and positive or large and negative. So clearly, if you substitute the value 0 for x, the first two terms here will vanish, we'll just be left with c. So that this is the y-intercept of the quadratic function. Now the value of the function at the point 1 also is simply a plus b plus c. That also can be useful sometimes. When x is 1, the value is just the sum of the coefficients. Now, as the value of x becomes increasingly large and positive, or large and negative, the value of a function is determined by two cases. If a is greater than 0, so that if x is becoming large and positive and a is greater than 0, this term here will be very large and positive, right? And it will outgrow the last two, so that the whole function will become large and positive. So that as x becomes really large, it doesn't matter which direction you go, because this first term will be positive. If you square any number, it will be positive. So this term will always be positive. And as x increases in magnitude, whether it's negative or positive, this term overall increases. So as you go to the left, the function also increases upwards. As you go to the right, the function increases. The second case is if a is a negative, then the function will go towards negative infinity. It will become large and negative, because if x squared is a positive number and it's increasing in value, if a is negative, whatever value you get for x squared will be large and negative, because of the value of a is less than 0. So the product of a negative value and a positive will always give you negative, but now it will be large in magnitude and will be moving towards infinity as you move on, like that. So using this expression that we obtained earlier, we can determine the maximum or the minimum value of the quadratic function as follows. If a is greater than 0, then we can see that the smallest value that the only thing that determines whether the function varies is this term, because x is the one that varies. This term is constant, right? So this term can only grow bigger if a is positive. As x increases, this term becomes large and positive. So the smallest value you can have is when this term is 0. When x is equal to minus b over 2a, that's the smallest this can be. And at that point, it gives this, we get the smallest possible value for the function f, and that will be the remaining term, which is this constant here, 4ac minus b squared over 4a. So this becomes the minimum value of a function, and the minimum value is usually will be attained when x is minus b over 2a, and that is when this part is equal to 0, this part of the function. So, but on the other hand, if a is less than 0, then what we have is that this part, the largest it can be is when x is, this term is 0, and that is also when x is minus b over 2a. Because otherwise, when a is negative, this term, as x goes to infinity, this term grows in magnitude, it becomes large and positive, but since A is negative, that will make the whole term large and negative, right? So it will keep decreasing. And the highest it will ever be is when this term is 0. That is when x is minus b over 2a. And when this term is 0, then the maximum value will be, again, 4ac minus b squared over 4a. And again, it is attained when x is equal to minus b over 2a. So with this, we're able to determine the maximum value of the function if a is negative, and the minimum value of the function if a is positive. Now we consider what happens to the function when we equate it to 0. So in this case, this is what gives us the quadratic equation. When you equate this function to 0, we get the quadratic equation. So we use the formulation we had earlier. So we can replace this term, ax² plus bx plus c. We can replace it by this because we showed that it can be written in this form. And we equate it to 0. So here a is not equal to 0 according to our definition, and we are multiplying a by some term, and we are getting 0. So whatever is in the brackets must be 0, which means we can just leave out the a, and that means this quantity must be equal to the negative of this, and that's what is expressed in the next step. So x plus b over 2a squared will be equal to negative 4ac minus b squared over 4a squared. So all this can be, if we multiply it throughout by the negative, we can rearrange this left-hand side, right-hand side to be b squared minus 4ac over 4a squared. We take the square roots on both ends, and we have x plus b over 2a will be plus or minus the square root of b squared minus 4ac over 4a squared. Now the square root of 4a squared is 2a, so we can simplify that, and we keep b squared minus 4ac under the square root sign. And on the other end, we still have x plus b over 2a. We can make x the subject of this so that we get the values of x for which this function is equal to 0. And when you do that, we end up with this. And this is what we call the quadratic formula. This one gives us the values of x that satisfy the quadratic equation, ax² plus bx plus c is equal to 0. So that's how you derive the quadratic formula, and it will come in handy. So these values of x are just the ones at which it cuts, the curve cuts the x-axis. So the value, if you look at this, we are getting the square root of some value, b squared minus 4ac. So the nature of the roots will be determined by the value of this quantity, which we call the discriminant. What we know is that we'll consider cases where this is 0, where it is positive, and where it's positive, it means you can get real roots. And where it's negative, it means you can't get real roots because a square root of a negative number is not a real number. You will get complex numbers, but we shall not do much on complex numbers for this. So when considering the discriminant, 3 cases will arise depending on the value. So we look at this in the following cases. We consider the, there we go. So we first consider the case where b squared is greater than or equal to 0. So in this case, we can get 2 distinct points. Minus b plus square root of b squared minus 4ac divided by 2a. And the second point would be minus b minus square root of b squared minus 4ac divided by 2a. So this gives us 2 distinct points when b squared minus 4ac is greater than 0. So we can see this in the diagrams as follows. So as a, if a is greater than 0, remember we said if a is greater than 0, as you go towards positive infinity, the curve goes towards infinity. As you go towards negative infinity, the same thing happens. The curve still goes towards positive infinity. So if a is greater than 0 and it cuts the x-axis at 2 points, the curve will be facing upwards like this. On the other hand, if a is less than 0, the curve will be facing downwards. So this is a case where it has two distinct roots and therefore must cut the x-axis at two distinct points. So this is useful when you're trying to solve inequalities. So for instance, if you want to consider values for which the graph is greater than 0, or the curve is greater than 0, then you'd consider points that are less than these points towards this end. And also for this case, points on this end will give you the intervals in which the graph is greater than 0. For this other one, the graph is greater than 0 only between the two distinct roots. If you call this x1 and this x2, the graph will be above 0 between those two roots. And that is when a is less than 0 and the curve is facing downwards. So the second case we look at is when b squared minus 4ac is equal to 0. And when this happens, the curve basically touches the x-axis at exactly 1 point, and that's the reputed root. So the term under the square roots, b squared minus 4ac vanishes, and we're only left with x is equal to minus b over 2a. So again, we see this in the figure below with different cases. So when a is greater than 0, the side on which your graph will sit is determined by the sign of b. If b is greater than 0, it sits on the negative side. If b is less than 0, it sits on this point will be positive. So it's the root will be positive. A similar thing happens on the other end, but a bit reversed. If b is less than 0 here, and a is also less than 0, then you have a negative root, repeated root. If b is greater than 0, then we have a positive repeated root. So on this end, we are considering the case where a is negative. And on this side, we consider the case where a is positive. And then check what happens for different values of b, whether negative or positive. So the third case is where b squared minus 4ac is greater than 0. And this requires us then to get the square root of a negative number, which you can write as complex numbers. So I will not dwell on this much, but this is how you obtain the complex roots of a quadratic equation. Use this new number I, which is defined as I squared is equal to -1. So I is a square root of -1, and it's an imaginary unit. So with that, you can always obtain complex roots of the quadratic equation. But this will not be the focus for the talk. So when you have the complex roots, it means the curves do not cut the x-axis at any point. So it's either completely above the x-axis or completely below the x-axis. It will be above if a is greater than 0 and below if a is less than 0. So now we consider the best from the quadratic formula. We can obtain two different roots. One of them is x1 is minus b plus square root of b squared minus 4ac over 2a, and the second one is minus b squared minus 4ac over 2a. Now, when you add these two roots and simplify, you end up with this relationship that the sum of the roots will be equal to the minus b over a. So this will always be true. The sum of the roots will always be equal to -b over a. And this is, you can easily see this by just adding the roots that are obtained from the quadratic formula and simplifying to end up with this quantity. The next thing we look at is a product of the roots of the quadratic equation. So if you multiply them, we'll make a small simplification. If we take t to be equal to this quantity, square root of b squared minus 4ac over 2a, then we can substitute it in the formula as t, the quadratic formula, so that we have two roots, x1 minus b over 2a plus t, and x2 will be minus b over 2a minus t. So those are the two roots, and if we multiply them, it will be as if we are multiplying a difference of two squares. Using the formula for the difference of two squares, we're able to rewrite it as b squared over 4a squared minus t squared. But we know what t squared is. It is this thing. If we square it, we'll lose the root sign, and this bottom will be 4a squared, and that's what we have here. And when we simplify all this, we end up with c over a. So the product of the roots will always be equal to c over a, which are the coefficients of the quadratic function. So we can make a few remarks. Since we know that the product of the roots should be c over a, if both roots are real, then they must be of the same sign if a and c are of the same sign. Why do we say that? If the roots have the same sign, then their product will be positive. That means c over a must also be positive, and that can only happen if c and a are either both negative or both positive. So if the roots, if they will be of opposite signs, again, if a and c are of opposite signs. So if the roots are of opposite signs, if you multiply them, you get a negative number. And for c over a to be negative, it means they also must be of opposite signs, so that their quotient c over a will also be negative. So this can help you make some conclusions about the roots once you know the signs of a and c. So now we look at how we can factorize a quadratic function. So we already have some knowledge about the roots. Suppose alpha 1 and alpha 2 are the roots of this quadratic equation. Then we know that alpha 1 plus alpha 2 should be equal to minus b over a, and alpha 1 multiplied by alpha 2 should be equal to c over a. So we know we can write this quadratic expression. We pull out the a, and we have x squared plus b over ax plus c over a in brackets. So we know the value of b over a. B over a will be the negative of alpha 1 plus alpha 2 in brackets. Because this is negative, I can just put the negative to this side and make the substitution. I substitute, so now I have b over a as negative alpha, the negative of the sum of alpha 1 and alpha 2. And I know the product is c over a, so I can substitute this c over a by the product, alpha 1 and alpha 2. So when I put it in that form, I can eventually split it, factorize it. X is common in these first two terms, so I can pull it out, and I have x multiplied by x minus alpha 1. Again, here alpha 2 is common, so I can pull out alpha 2, and I'm left with x minus alpha 1 in brackets. And that gives me ax minus alpha 1 in brackets multiplied by x minus alpha 2 in brackets is equal to 0. So now this gives me two factors of the quadratic equation. And this is how we factorize. So now if you just had this, to find the factor, sometimes you just have to use trial and error, which means you first of all find two numbers which when multiply will give you this quotient, c over a, and another two numbers which when added will give you this quotient, b over a. So this, when we are looking for, when these are rational numbers, in other words, if c and a are integers, then this makes a lot of sense. But if they are not, then it may not make a lot of sense. But if it turns out that the roots are integers, then our work may become a little easier. So if a is equal to 1, then your we can lose the a, because let's just go back one step. We see we have the a out here. So if a is equal to 1, we're only left with the term in the square brackets. So that if a is equal to 1, we have x squared plus bx plus c is equal to 0. And we know that this can be written as x minus alpha 1, x minus alpha 2 is equal to 0. So if b and c are integers and we want to find the roots or to factorize this expression, all we have to do is to find two integers, alpha 1 and alpha 2, whose sum is equal to b minus b rather, and the product would be equal to c. So that should be the strategy if you want to find the roots. So this process can be quite tedious depending on the value of c. C can have many factors, and that can be quite tedious sometimes to work out. There's a method that makes that easier, that takes away the guesswork out of this, but we shall not cover that in this lecture. Maybe next time we shall do it. But you can find this on the internet. It was covered by the team leader for the American team to the International Math Olympiad. He's called Paul Shenlo. There's a video on YouTube on his method on how to find the factors without having to worry trying to check for factors of C. You can factorize a quadratic equation by just a very direct method. I will not cover that now. Maybe we can organize for a talk where I cover that, but it's a very direct method and takes a lot of guesswork out of finding the roots and eventually factorizing the quadratic equation. So even if they're integers, this may not always happen. And if that doesn't happen, we will be forced to use a quadratic formula. So the other ways you may solve a quadratic equation, you could draw the graph, but this will heavily depend on how accurately you can draw it, and you can get some approximate values of the roots. Factorization, we have seen it can be done also. Once you find the factors, you can find the roots as alpha and beta, and you may also use a quadratic formula. This, I think, is a mistake. This should be b squared minus 4ac to find the root. So I think this should be minus b plus or minus square root of b squared minus 4ac. I think that is still fine.
Still fine. No, it's okay.
Yeah.
It's okay.
But why did I put the negative? Okay.
It's just okay.
Yeah, it is fine, but it's okay. We'll work with that. So using the properties covered in the earlier section, we can now look at some important features rather of the curve. So we can find the y-intercept easily, and we have also checked what happens when x becomes large and negative or large and positive, depending on the value of a. If a is positive, the curve faces upwards. If a is negative, the curve faces downwards. And the roots also are the points at which it cuts the x-axis. It may or may not cut the x-axis, and this is determined by the discriminant, as we saw earlier. So once we go through all such features, it is possible to do a rough sketch of the curve. Now we'll go to some examples where we can use some of the information we have learned. So I don't know how we're doing on time. I think we're okay. So this first example says, describe the important features and sketch the graph of f of x is equal to x squared minus 3x plus 5. So clearly the y-intercept will be 5. That's the value of a function when x is 0. Now, since a is positive, we see a is equal to 1 in this case, and it's positive. As x becomes large and negative or large and positive, the function still becomes large and positive. fx always goes upwards, keeps getting larger and larger, regardless of which direction x is going. If you apply this formulation for the quadratic expression, we can find the minimum value for the function. Remember, when a is greater than 0, we have a minimum value, and that minimum value is usually this term. When we work it out, we get it to be 11/4. So the minimum value is 11/4. And this is attained when x is -3/2, I think. So I think that's correct. When x is 3/2, not -3/2.
At 3/2.
Yes, when x is 3/2. So that gives us a minimum value. So with this information, we can actually sketch the graph as follows. Before we sketch it, we didn't check the discriminant, but you will realize the following. The graph never goes below the value of 11/4. So it will never cut the x-axis. That's another thing we should have pointed out. So it never goes below 11/4. So if you draw a line at the point on the y-axis 11/4, the curve stays strictly above that. So that's the sketch of the curve. Minimum value is at when x is 3/2, and the value at that point is 11/4. This is a y-intercept, 5, and so on. And the graph, it faces upwards. And it's completely above the x-axis. So we look at the next one. We describe the important features and sketch the graph of x² - 5x + 6. Again, we get the y-intercept, which is 6. We notice that, again, a is positive. So if when x becomes large and negative or large and positive, the quadratic, it should be g of x here, goes to infinity. It also becomes large and positive. If we put it in this form, I think this is correct. This should be greater than, I think. Huh? There's a, it should have a minimum value of -1/4. So it should exceed -1/4. I think that's, it needs to be corrected. So, and that occurs when x is at 5/2. Now, if we equate it to 0, since now we know it's going upwards and there's a negative minimum value, so as it goes up, it must cut the x-axis. It means we can find the roots. You can also check that it has roots by looking at the discriminant. And if we equate it to 0, then we can, it means x minus 5/2 squared will be equal to 1/4, or, and this simplifies eventually to x is equal to 3 or x is equal to 2. You could also just use the roots obtained from the formula or otherwise, and you have x minus 3, x minus 2 is equal to 0. And the graph will look like this. It will cut the x-axis at 2 distinct points. So the next example does something similar, but this time the value of a is negative. So again, the y-intercept is -1. As x becomes large and positive or large and negative, the value of a function becomes large and negative because a is less than 0. A is -1. So that is what happens. So this means the curve will face downwards, and it has a maximum value of 0. Again, this is a mistake. This should be a maximum value. It has a maximum value of 0 at x is equal to 1. So the curve will face downwards. and that's what you get. So these features will help you quickly sketch the graph and know once you find the relevant points and you know the sign of A, you're able to sketch the graph and pull out some of its properties. So it has a repeated root in this case. It touches the x-axis at exactly 1 point. And again, if you check the discriminant, it will be equal to 0. And that's another way of confirming that it has exactly one distinct root. So here is an example where we were looking for the real roots of the quadratic equation, 3x² plus 4x minus 3 is equal to 0. We apply the quadratic formula. We just need to identify our values of A, B, and C and make the substitutions in this formula. And when we do that, we end up with these two values, minus 4 plus or minus square root of 52, all that divided by 6. So you can use your calculator and confirm that to 3 decimal places, these will be the values of x. And we can sketch the graph. It has two roots. One is negative, and the other one is positive. And it will go upwards because it will face upwards because the value of A is 3, and 3 is a positive number. So here it's a similar situation. We are finding the real roots. Here we have A is equal to 4, B is equal to minus 28, and C is 49. And if you apply the quadratic formula, you see the discriminant here will be 0. If the discriminant is 0, you have a repeated root. And our root will be x is equal to 3.5. So this is repeated. And you can sketch this like that. It has a repeated root and will be facing upwards. So that shows you where the root is, about 3.5. So this one asks us to find the real roots of x² minus x plus 1 is equal to 0. And when we use the quadratic formula, we end up with the square root of a negative number. The discriminant is negative, so we have the square root of a negative number. So it means this one does not have real roots because the square root of a negative number will not be a real number. So we can't find any real roots for this quadratic equation. And you can see from the sketch, it doesn't have any real roots, and therefore it's completely above the x-axis. That happens if A is greater than 0. So it's completely above the x-axis. So here's another example that is more theoretical. It says if alpha and beta are roots of a equation ax² plus bx plus c is equal to 0, find the values of, we have 3 problems to solve. One is to find the value of alpha squared plus beta squared. The second is find the sum of the reciprocal of alpha and the reciprocal of beta. And the third is to find the sum of alpha cubed and beta cubed. So we shall do this step by step. So the first one requires us to find alpha squared plus beta squared, I think. Let's just go back to confirm. Yes, the first one is alpha squared plus beta squared. So we recall some properties we had earlier that the sum of the roots will always be minus b over a, and the product will be c over a. So we rewrite this in such a way that we, in terms of the sum and the product, and alpha squared plus beta squared can be written in this form, alpha plus beta squared, and then you have to subtract 2 alpha beta. And simply make the substitutions. Alpha plus beta is minus b over a, you put that here. And alpha beta is c over a. So when you make those substitutions and simplify, we find that alpha squared plus beta squared is the same as b squared minus 2ac over a squared. So the next one, again, we have to find the value of the sum of the reciprocal of alpha and the reciprocal of beta. So we write this as alpha plus beta divided by alpha beta, and again make the substitutions for the sum and the product of the roots. And this simplifies to minus b over c. So the third is alpha cubed plus beta cubed is equal to alpha plus beta. This is one of the identities we wrote down at the beginning. So we're able to get the first factor here as the sum of the roots. Then we have a quadratic term in here. So this quadratic term can be written as alpha plus beta squared minus 3 alpha beta. You can confirm that. And now we have everything in terms of the sum of the roots and the product of the roots. So we can make our substitutions. Alpha plus beta is minus b over a. Alpha plus beta squared is just b squared over a squared, and minus 3 alpha beta is minus 3c over a. And after a bit of work, this simplifies to b multiplied by 3ac minus b squared over a cubed. So that answers all the three problems. Based on the properties of the roots, we've been able to find those values in terms of a, b, and c. So here is an example for projectile motion. If a stone thrown vertically upwards with an initial speed of 20 meters per second is at a height y meters above the point of projection after t seconds. Now, if y is given by 20 minus 5 t squared, for how long is the stone more than 10 meters high? So we have an inequality here that we need to solve. We know that the height is given by 20 minus 5 t squared. We want this height to be more than 10 meters. So if we set up this inequality and solve it, we'll find the values of t for which this function is more than 10. And that is all we need. If you can find those two values, the difference between those two values will give us the time for which the stone is above 10 meters. So we can rewrite this, if we write this function as f of t is minus 5t squared plus 20. Something is not right. I think I left out a t here. There should be a t, 20, I think it should be 20t minus 5t squared. There's a problem with the question. So if you write it out like this, then it becomes a quadratic function, and you know the y-intercept is minus 10. F of t is 0. The roots now will be obtained by solving this, equating it to 0 and solving it. And we find the root to be 4 plus or minus square root of 8, all that divided by 2. So once you find the roots, we can sketch the curve. So we need to know when this function is above 10, and it's above 10 between the first root and the second root. So you simply get the difference between the first root and the second root, and that difference is actually the square root of 8. You can check that by the first root will be 4 plus square root of 8 over 2, and the second root will be 4 minus the square root of 8 over 2. So the difference between the two roots is just the square root of 8, and we conclude that the ball is above the 10 meters for that much time. After that, it will be below. Here is another example for solving by completing the square. So completing the square simply means turning this into a perfect square, and any time that you have to add on this end to turn it into a perfect square, you have to add to the right-hand side as well to complete. And that's what we do here. So, but we divide throughout by 2 so that we have x squared plus 4x is equal to 3. And then we complete the square on this side to have x plus 2 squared. But since we added 4 to complete the square, we must add it on the other side as well. But x plus 2 squared will be equal to 7. And x plus 2 will be plus or minus root 7. So the roots will be x is equal to -2 plus or minus the square root of 7. That should solve the problem. So here are some exercises for you. If you can note them down and try to solve them on your own. That brings us to the end of the talk. Thank you very much for joining us today. And we can take some questions now. Comments, questions?
Asante sana.
So it would be good to get some feedback. So here we went through a whole topic. Would like to know if you learned anything new, if it made your understanding of a quadratic equation any better. Hopefully not any worse.
Daktari, I think that it was good. The only thing is when we talk about f of x, for some of the students, you need to help them connect with f of x. They are used to y is equal to. So they just need to move into y is equal to can be replaced with f of x so that they're able to make the connections more easily.
Okay, thank you for the comment. I hope the students have heard. You simply replace f of x with y for any, if you're facing any difficulties in understanding. Thank you for that comment, clarification. Anything from the students or any other participant? Yes?
The talk was good, good Daktari.
Okay. So is there any topic you think we should cover next? What if I suggest trigonometry? Would that be a good topic to cover as the next topic?
Yes.
Yeah, it's a good topic, sir.
Okay. So also as we cover the topics, we'll cover it in a little more detail, sometimes going a little beyond what is covered in the standard syllabus. But hopefully that will be still make you understand what you cover in the syllabus better. So the floor is open for comments. If you have any comments, please go ahead and
Just a question, Daktari.
yes, Vincent.
Will be the training be is it weekly or
so
daily?
Okay.
Or?
The training is every 2 weeks. So the next training is in 2 weeks' time. We have it on Monday, every 2 weeks from 7 to 8 p.m.
Okay.
So usually once you register and get the invitation, it should be able to, you can put it on your calendar. If you have a Google Calendar, it should send you a reminder.
So when is the competition?
Oh, so the next round of the KKMO Mathematical Olympiad will be in June. We are hoping everything goes well. There are a lot of things happening around with the COVID, But if everything goes as planned, we should have the competition on 10th of June, the first round. And that should be done in the school, so there'll be no traveling, and that should be safe. We hope to have many more participants, but the aim of these classes was to cover some of the topics and some of the questions that are Olympiad based, so that we can get people more interested in the competition. And the second thing is it also gives us a chance to add more value to the whole setup, the interaction beyond just those who participate in the competition. So this one is open to everyone, whether you participate in the competition or not. You still get to learn more about the mathematics.
Yeah, so I'm seeing your recording. So how can we get the recorded video?
So I will get the recording and process it. I think in 2 days' time, I will have that done. I have the recording for last time, the last two. I will share those as well. The first one is already up on YouTube. I don't know if I have the link. Let me try to find the link, then I can share with you the first recording. In the meantime, if you have any questions, you can ask. If you have any comments, you can make as I look up the link.
Yeah. You can mention to them that the product root property is better.
The what?
Its identity. The product sum.
Oh, okay. Just repeat that again. You can mention that.
The products, such that the product of the roots and the sum of the roots, that property is called Its identity.
Oh yes. Yes. If we have some time, maybe we'll cover polynomials of higher order, and then you'll encounter the same ideas about the roots, the sum and products of the roots. Yeah. So it's thank you for that. Yeah, it's called Viets. Some people call it Vieta. Some people call it Viet.
Maybe just on the same. Huh?
Yes.
Maybe after such a perfect presentation, maybe you can give them more questions to try on the same. Just play with the quadratic equations.
Yeah, I think I will do that. There are only three that I've put there, but we can create more and add.
So really, it's really a powerful tool you can use to solve many questions.
Yeah. Okay. Fine. That is noted. I think that would be a good addition to this. So I'm putting the link to the first talk that we had. It's there in the chat. If you check the chat, you will be able to find it. Now, I also did another video on differentiation, but that one was pre-recorded. It was not live. I don't know if I can track it easily. Yes, I'll put it also in the link. This one was pre-recorded. So the code. So here. I've put the link there in the. That one is just the first part of a series I was doing on differentiation. I will complete it so that we have a complete series of those videos. Now we already passed time, but if you have any more questions, you can ask before we close. So thank you very much for joining us today. I wish you all a good night, and look forward to seeing you again in 2 weeks' time. We will be looking at trigonometry, and I will try to make available some more questions for practice. Thank you.
Bye.
Bye.
Goodbye.
Good night, sir.
Bye. Good night, sir.
Okay. Bye-bye.
Bye.
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 Bye.